Hello everyone. Welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our last session, we have discussed about gradient descent algorithm, and we have got to know that for the weight updation in the neural network, we need to find out the gradient of the loss function. Now, in today's session, we will study the algorithm through which this gradient of loss function is found mathematically, and this is called as the backpropagation algorithm in neural network. So today's my session will be entirely focused on backpropagation in neural network. To start with, let us have this setup. So I have an input layer, and then in the input layer there are input neurons x1, x2. Then I have the hidden layer which are shown here z1, 1, z2, 1, z3, 1. Now if we see the edges connecting x1 to z1, x1 to z2 or x1 to z3, they are having the weights w11, w12 with a superscript 1. That means this 1 in the superscript shows that they are belonging to the first layer. Okay. So after this hidden layers z1 calculation, which is nothing but the weighted sum of the inputs, then we have given an activation function which is the sigmoid activation function here, which operates over z11, z1, z21, z31, and then whatever is the output, again those goes to the output layer neuron. There is only one neuron in this output layer, and the associated weights are given by w112, w212 and w312. So here the superscript 2 means that it is in the second layer, and z12 means it is in the output neuron. Okay. And then z12 goes through once again through the sigmoid activation function, and then we get the output as y. Okay. So this is a toy neural network that I have taken for explaining the backpropagation algorithm. Okay. And we know the loss function is actually the difference between the actual value and the your predicted value, correct? So the actual value minus y if y is your predicted value, and t is, if it is your actual value, then t minus y is your loss. Okay. Now we will have this toy neural network schematic of this one here in all throughout the slides, and then we will do the mathematical calculation side by side. For simplicity, I have taken the loss function here, so I'll just write it here. 1 minute. So I have taken the loss L is equal to the mean squared error which may change in your actual application. Of course, it will change. Here for simplicity I have taken, and which is nothing but 1 by n. We all know summation over I equal to 1 to n, and then we have yi minus yi hat square. Okay. So and 1/2 term we will add here for mathematical convenience, and what we know here is 1 by 2n. Now it becomes then summation I equal to 1 to n. Your yi is nothing but your ground truth, which is your t, minus your predicted value, which is your y square. Okay. This equation we will keep as equation number 1. Now what is n? N is the number of observations, we all know, and half I have told that we have taken for some mathematical convenience. Now according to gradient descent, we need to calculate what we need to calculate according to gradient descent. We need to calculate the gradient of the loss function, right? So, gradient of L with respect to L, which is a function of W and B. And this we require for weight updation, okay, for weight updation. Fine. Now, backpropagation algorithm is a structured way to get this gradient of L with respect to your weights, okay. So, what we will write here is gradient of L with respect to the weights is equal to partial derivative of L with respect to the weights when L is a function of both weight and bias. Now, if you see in this figure, there are a lot of weights, okay. So, we have W111, then W121, W221, and then we have W112, W212, W312. So, there are a number of weights are associated with this network, okay. So, in order to calculate the gradient of the loss function, here we need to calculate the partial derivative of the loss function with respect to all the weights, okay. So, and also before I start into the calculations, we will see that as loss is calculated here. So, it is, you know, the loss comes here, correct, loss equal to your target minus your whatever your predicted 1 by n summation whatever, okay. So, as it is calculated here, what we do is we will try or we will do the propagation of the error from the last part of the neural network towards in the backward direction, okay. Now, we will try to find out what is the gradient of the loss function with respect to this weight W112, okay. So, we will calculate that one. So, let us calculate partial derivative of L with respect to del 112. This I want to calculate. Now, partial derivative of L with respect to del the weight in the last layer, I can write it as del L by del y into partial derivative of y with respect to 112. This we can write, okay. This I will name as equation 1.1 because we will be coming back to this equation. So, just to keep a track of that. Now, from equation 1, we get del L or partial derivative of L with respect to y is nothing but 1 by 2n summation 2 into t minus y into minus 1, which is equal to nothing but 1 by n summation y minus t. So, this is your partial derivative of the loss function with respect to y. So, this I will put as 1.2. Now, we have done this, we have calculated, correct. Now, we have to calculate the second. This we need to calculate now. How do we do that one? So, we have to calculate now partial derivative of y with respect to W112. If we see what is my y? Y is nothing but sigmoid activation function working on Z1, 2. Now, if we have sigmoid activation function, sigmoid function working on x, we know the formula is 1 by 1 plus e to the power of minus x. If I take the derivative of this one with respect to x, what I get is this, I can write it as 1 plus e to the power of minus x to the power of minus 1. Then the derivative I can write as minus 1 plus e to the power of minus x to the power of minus 2 into e to the power of x, which is nothing but into minus 1, sorry, which is equal to e to the power of x by 1 plus e to the power of minus x whole square, e to the power of minus x divided by 1 plus e to the power of minus x whole square. Now, this can be written as sigmoid of x 1 minus sigmoid of x. You can do it and then cross verify it. Now, this equation I will mark as 1.3. Fine. Again, coming back to where we left it, your y is nothing but the sigmoid of z1 2. Okay. Therefore, your del y or partial derivative of y with respect to W112 is equal to, I can write it as sigma z1 2 by z12 into del of z12 by del omega 112. Okay, this we can write. Now, if we see, this is the derivative of sigmoid function working on z1 2 in the second layer. So, according to equation number 1.3, we can write this as sigmoid of z1 2 into 1 minus sigmoid of z1 2 into the same third term, whatever is there here, 1 1 2. This is coming from equation 1.3. Okay. Now, what is my sigmoid of z12? It is nothing but equal to y. This is my y. Therefore, I can write del y omega 112 equal to y into 1 minus y into partial derivative of z12 divided with respect to W112. Okay. Now, what is my z12 made up of? Now, we can write z12 can be written as, see, if we see here, it is this output multiplied with this weight plus this output multiplied by this weight plus this output multiplied by this weight. If I write this one as H1 for convenience, this one as H2 and this one as H3, then Z12 can be written as H1 W112 plus H2 W212 plus H3 W312. Okay. Now, what is your H? H is nothing but H1 is nothing but your sigma Z11. H2 is equal to sigma Z21. H3 is equal to sigma Z31. Okay, done. Therefore, what I can write? Therefore, I can write partial derivative of y with respect to W112 is equal to y into 1 minus y. This I have got already. I am using that one into, for the third term only h1 is coming. Okay. So, this is my partial derivative of y with respect to W112. Putting all these values in equation 1.1, we get, what was our equation 1.1? That was the full equation for getting the partial derivative of the loss function with respect to W112, which was our starting problem statement. Okay. So, we can write partial derivative of L with respect to W112 is equal to 1 by n summation y minus t into y 1 minus y into h1. So, this is how we get, you know, the partial derivative of L with respect to this weight. Now, as I told, for gradient descent algorithm to work, we need to find out the gradient of we need to find out the partial derivative of the loss function with respect to all the weights in the network. So, similarly, we can do it for, you know, a partial derivative of L with respect to W212, partial derivative of L with respect to W312, and so on. So, I have shown one for this layer, the output layer, whatever is going in the output layer. So, that portion. Now, I will take another one, which is, I want to show something. How do I get the partial derivative of L with respect to W111, because that also is required. These are all 111, 121, 131, 211, 221, 231, all are weights. These are the weights associated with the, you know, first layer, that is between the hidden layer and the input layer. So, now I will show how we can get this. Now, let us calculate, I will write it. Now, let us calculate partial derivative of L with respect to W111. What is W111? That is here. So, we have to do this one. We will write partial derivative of L with respect to W111 as del L by del H1 into del H1 by del W111. What is my H1? H1 was this one, this was my H2, and this is my H3. So, I have written the partial derivative of L with respect to W111 as partial derivative of L with respect to H1 into partial derivative of H1 with respect to W111. We have started for the, you know, layers which are inside, we start from the, you know, nearest layer, and then what we will do is we will use whatever we have calculated for the, you know, the layers which are near to the output. Now, we have seen, okay, what is H1, H2, H2 we have seen. Now, H3 we have seen. Now, what we will do is del L by del W111, I will write once again as partial derivative of L with respect to sigma Z11. Why I am writing this one? Okay. So, because your H1 is nothing but your sigmoid activation function working on Z11. Okay. So, for H1 I have written it here. Then del of sigmoid of Z111 into partial derivative of Z11 with respect to 111, W111. Okay. So, this I will put as equation number 2. Here we will keep the first term as it is, del L by del sigma Z1 1 into this one. Once again I can see it is derivative of the sigmoid activation function. So, this I can write as sigmoid of Z1 1 into 1 minus sigmoid of Z1 1. This is from equation 1.3, I remember, from equation 1.3. That the derivative of a sigmoid function is, it can be written as sigma x into 1 minus sigma x into the last term. I will keep it as it is, Z1 1 with respect to W111. Okay. So, I will continue writing this one as partial derivative of L with respect to sigmoid of Z1 1 into H1 into 1 minus H1 into X1. Okay. So, why I have written H1 into 1 minus H1? Because your sigmoid of Z1 1 is nothing but your H1. And how have I written this X1 term? From where this X1 term came? X1 term came from my third term, which is del Z1 1 del omega 1 1 1. So, if I see it here, it is nothing by, what was my Z1 1 1 made up of? Z1 1 was, what is this? Now, Z1 1 is made up of W111 into X1 plus W211 into X2. Therefore, del Z11 with respect to omega 111 is nothing but equal to X1. Okay. That is the reason I have written this X1 here. Fine. This equation I will write as equation number 3. Okay. So, and what were we calculating? So, I will just write it here. What did I get finally? Partial derivative of L with respect to W111 is equal to partial derivative of L with respect to sigmoid of Z11. This I have kept as it is. The remaining two terms I have got the values H1 into 1 minus H1 into X1. So, this is my equation number 3. I will not write it there, equation number 3, I will make it here, so that there is no confusion. Okay. All right. Then, for finding out the partial derivative of L with respect to W111, we are still left out with finding out or calculating this term. Next two terms, the other two terms we have already done. What do I do for that? So, we will try to figure out what it is. Partial derivative of L with respect to sigmoid of Z11, which I will write it as del L by del H1, because this is nothing but your H1. Okay, this is nothing but your H1 value. This can be written as del L by del Y into del Y by del Z1 2 into del Z1 2 into del H1. So, what I am doing here is I am using whatever I had done in my previous steps. Z1 2 is nothing but this one. So, this I had used when I was doing the weight updation or the partial derivative calculations for W112. So those things now I will use it. So we are going in the from the front to the backward direction. Okay. Now we know del L by del y is nothing but 1 by n summation of y minus t. This is from equation 1.2. So the second term, so this is the first term, this is your first term. The second term, what is the second term? Partial derivative of y with respect to z12. What is your z12? Sorry, what is your y here? That is nothing but sigmoid of z12. Okay, make this one a little clear. Yes. Okay, so y was nothing but the sigmoid of z12, which I have written here, and I am taking the derivative of y with respect to z12. This again I can write as sigmoid of z12 into 1 minus sigmoid of z12 from equation 1.3. That is nothing but equal to y into 1 minus y. So second term also we calculated. First term we got here, second term also we calculated. We are left only with this one, the third term. So let us see what we can do to find out third term. So the third term, what was the third term? Partial derivative of z12 with respect to h1. If we see what is my z12 made up of, it is sigmoid of z11 into w12 plus sigmoid of z21 into w212. So I will write it, plus sigmoid of z31 into w312. So if we take the partial derivative of z12 with respect to h1, once again I will write it h1 here, it is h2 equal to h3 here. So I have to find out here this one. So I will just write down once more, z12 equal to h1 into w112 plus h2 into w212 plus h3 into w312. Therefore, if I take the partial derivative of z12 with respect to h1, I get w112. Therefore, so first, second and all the third term, all three we have calculated now. Therefore, we can write del L by del h1 equal to 1 by n summation y minus t into y 1 minus y into w112. Now, taking all the previous values here. Putting all these equations, putting all these values in equation 3. What was our equation 3? It was the one partial derivative of L with respect to w111 with respect to this one. We get, what do we get? Partial derivative of L with respect to w111 is equal to 1 by n summation y minus t into y into 1 minus y W112 into H1 into 1 minus H1 into X1. Okay. So, taking all these values from first term, second term and third term, we get this one. 1 minus y minus t into, yes, y into y minus 1, W112, and then from the previous term we got H1 into 1 minus H1 into X1. Okay. So, we have got, finally we have got the partial derivative of L with respect to W111, which is a weight in the inside layer, okay, between the input node and the first hidden layer. Now, if I want my gradient descent algorithm to work, I need to find out something called as grad of L. So, if I write W1, let W1 be all the weights of your first layer. So, all these I put them in the form of a vector and I can write it as W111, W121, W131, so on, W211, W221, W231. Okay. So, if you have some more, if you write it like this, then gradient of L with respect to the weights can be written as del L by del W111, 211, 1, partial derivative of W12, partial derivative of L, what is it? Partial derivative, yes, partial derivative L with respect to W1, 2, 1 and so on. Okay. Continue. So, after every iteration, we want to update the weights. So, after every iteration, weights will be updated. And what is the equation for that one? Weight at time t plus 1 or tau plus 1 equal to weight at the iteration one iteration before minus learning rate into the gradient of the loss function with respect to the weights at the time. This is W at this derivative of L with respect to this W. This W is nothing but at the time t, tau. Okay. So, the derivative is taken at W equal to W tau. And similarly, the bias terms also will get updated. P tau minus eta, that in that case your gradient will be taken with respect to the weights, gradient of the loss function with respect to the weights. Okay. So, this gradient will be taken at W equal to W tau. So, this is the way your backpropagation algorithm works, and we have seen that we have started from the output loss. Then we have come one layer in. Using those, we have found out the derivative of the loss function with respect to the weights that are present in the inside layers. So it is a propagation, or the error is propagated in the backward direction. Then that is the reason it is called as backpropagation algorithm. So with this one, I come to the end of today's discussion. Just to summarize what we have discussed today, we started with a toy neural network which we have set up for explaining the process of backpropagation, how the partial derivatives of the loss function are calculated with respect to the weights of the neural network. In the toy network, we have taken very simple activation function like sigmoid activation function and very simple loss functions like mean squared error, and we have shown the calculation of gradient of loss function with respect to one of the weights, or the partial derivative of loss function with one of the weights in the last but one layer, and then we have taken again the partial derivative of the loss function with respect to another weight which is there inside in the internal layers. So with this understanding, we will be able to do the partial derivative calculations of the loss function with respect to all the weights that are there in the neural network. The similar way, the bias also gets updated, and we have seen how the weight updation happens at the end of the gradient descent algorithm also. So that's the end of today's lecture session. I hope you have understood the mathematical formulation of backpropagation, why it is called as backpropagation, where all we are using the backpropagated errors in finding out the gradient of the loss function. So with this one, I come and conclude today's session. In the next session, we will talk about variants of gradient descent algorithm and momentum based optimizers which are used in machine learning model. Till that time, keep learning. Thank you all.